Okay, good morning, everyone. Today I'll be giving a talk on graph signal processing. Um, I'll be going over the basic properties of graph, the adjacency weight matrix, the Laplacian and eigenvalue decompositions, and a brief overview of the vertex clustering method in graph signal processing. Graph signal processing extends the concepts of classical time signal processing on graph data structures. For in classical time domain, where the signals are equidistant from each other, it's a bit of a limited, but in graphs, the signals can be present in irregular data domains. So it can be extended over irregular graph topologies. In that case, we can use graph signal processing. Then graph topologies are irregular structures consisting of vertices and edges. Graphs are irregular data domains where the graph signals can be considered as the data on the vertices, and the connections between the vertices are established by the corresponding edges. We can use MATLAB toolboxes such as GSP box, and in Python we have PyJSP, which can be used for processing data on graphs. For the graph properties, in graph, basically we have vertices and edges. So if G is a graph, we can consider V as a set of vertices and E as a set of edges. We can have directed as well as undirected graphs. For a given set of vertices, a graph can be represented by its adjacency matrix, and it also can be represented by a weight matrix. And we can use them both for directed and undirected graphs. The degree matrix of an undirected graph is a diagonal matrix with elements dii, which is the sum of the weights of all the edges connected to the vertices I. In adjacency matrix is a matrix where it has elements of only 0 and 1. So if we have two vertices and there's an edge connecting between them, then the element of the adjacency matrix will be 1. Otherwise, if there are no edges connecting vertices, then it's 0. For the weight matrix also, it's a similar concept. It's a n cross n matrix with n vertices with elements wij. And in this case, if there is no edge between two corresponding vertices, then the element wi will be 0. And if there is an edge between two vertices u and v, then it's equal to the element weight. It will be equal to the weight of that edge connecting those two vertices. So we can see that the adjacency matrix is an extension of the weight matrix, where instead of the weight, we can use 1 in adjacency matrix. The adjacency matrix and weight matrix of an undirected graph is symmetric. We also have a Laplacian matrix. So in case of graph, the Laplacian of a graph is given by D minus W, where D is a degree matrix and W is a weight matrix that is mentioned in the previous slides. The elements of the Laplacian matrix are non-negative real numbers at diagonal positions and non-positive real numbers at other positions. So the Laplacian matrix can have both negative and positive numbers as its elements. And like the degree and the weight matrix, the Laplacian matrix of an undirected graph is also symmetric. We can use the normalized Laplacian matrix formula because it's more efficient than the Laplacian one. And it's given by I minus d to the power minus half, W d inverse minus half, where I is the identity matrix. And then we can use the eigenvalue decomposition of the adjacency matrix, where the graph spectrum can be analyzed by this eigenvalue decomposition. The eigenvalue decomposition of the adjacency matrix is given by AU equals to lambda U, where U is the eigenvector of the adjacency matrix. It's a column vector, and lambda is called the eigenvalue of the corresponding eigenvector. It's a constant. The set of eigenvalues of the adjacency matrix is called the graph adjacency spectrum. Similarly, we can also have an eigenvalue decomposition of the Laplacian matrix. The graph spectral analysis can also be done by using eigenvalue decomposition of the Laplacian matrix, like we did with the weight matrix. The eigenvalue decomposition of the Laplacian of a graph with n vertices is LUK equals to lambda k into UK, where U is the eigenvector of the graph Laplacian and lambda is the corresponding eigenvalue of the graph Laplacian. for k equals to 0 to n minus 1, where we have a graph of n vertices. The set of eigenvalues of the Laplacian matrix lambda k is also called the graph Laplacian spectrum. So if for a graph signal, we have the basic structure of a graph. We have the vertices and the edges. And then the signal on the vertices can be considered as the data residing on the graph. And the signals are interconnected to each other by edges. So this is a basic structure of a graph signal in the graph domain. Now for vertex clustering is, we can say that it's one kind of graph learning where the vertices are grouped together to form a cluster. Vertices that are clustered together, they will exhibit similarity, large degree of similarity among themselves. So there are several methods to do the clustering. It can be done based on graph topology, and also it can be done based on eigenvectors, which can be called the spectral method of graph clustering. Clustering plays an important role in machine learning and pattern recognition research areas. Spectral-based clustering. So as mentioned, spectral-based graph clustering is based on the eigenvectors of the graph Laplacian. This method employs the several smoothest eigenvectors of the Laplacian. Sometimes we can also use algorithm which uses only one eigenvector, which is the second eigenvector of the Laplacian U1, also known as a fiddler vector. Graph clustering, which are based on this fiddler vector, will give an accurate and efficient clustering results in a range of applications, including data processing on graphs, machine learning, and computer vision. However, we can also use more than one smooth eigenvectors in the clustering method, and the partitioning also will give more physically meaningful clusters. So in this talk, just an introduction to the basic graph structures have been discussed. And we can see that in order to process data that are defined on irregular domains, such as social network, sensor networks, we can use graph signal processing, where the classical time domain signal processing won't work. Graph signal processing has many applications in the field of data analysis and computer visions. And in future, it also has many other topics like Fourier transform, graph filters, and dimensionality reduction, subsampling, which can also be discussed. So that is all. If you have any questions, let me know.
Are there any questions for the speaker? Or also feedback as well, like if you have any suggestions for how if you think there might be things that can improve the way that the person is doing their presentation, this can also be quite helpful too. So don't restrict your any discussion to just questions. If there's feedback you might have for the speaker in terms of how to improve from your point of view, that would also be helpful.
I have one question.
Yes.
Do you know how to do you know the common way to calculate the Laplacian matrix of the indirect map? So I from my understanding, I think only the symmetrical matrix adjacency matrix can be used to compute the Laplacian matrix, since only the symmetrical Laplacian matrix can be used to compute the eigenvalues, since it has to be symmetrical to get valid eigenvalues and associated eigenvector. So when we have an undirected graph, what is the common strategy to get to eigendecompose those Laplacian matrix?
For Laplacian, if it's symmetric or asymmetric, we can use in MATLAB, we can use the EIG function to get the eigenvalue decomposition. So if we have a graph, we can construct the Laplacian matrix using the formula D minus W. And then if you want to find the eigenvalues of those Laplacian matrix, you can use the eigenvalue function of provided by MATLAB to give those values of eigenvector and eigenvalues.
So my question is, if the graph is undirected, so the Laplacian matrix won't be symmetric. So, and then if we are going to decompose a undirected graph, we won't get a positive eigenvalues. We will get some negative eigenvalues, which is useless in graph signal processing, I think. So, well, it's okay if you don't know. So I just want to know if there are any common strategy to calculate, to handle undirected graph.
For the negative eigenvalues, I'm not aware of any methods to make them useful in the graph signal processing or not. But for clustering methods, you can just use one eigenvector instead of using all the eigenvectors in order to, if you want to do vertex clustering.
Okay, so makes sense.
Any other questions? I have a few like feedback I can provide. These are not really questions, but one thing I would recommend is whenever you're giving a presentation to always number the slides. Okay. It's off. It could be maybe things are just displaying wrong on Zoom and maybe the bottom of the slide is cut off, but if there's no numbers on it, it's very helpful because when you ask for questions at the end, it's often very helpful if people have questions as you're going along. Typically what they'll do is they'll write down the slide number and then like a note about the question that they have, so that then it's easy for you to refer back to the slide. But at least on my screen, there's no slide numbers appearing. So that would be one suggestion I would make. Another thing would be when you're talking about equations or particular parts of the slide, I'd recommend that you move your mouse to that part. Sometimes you seem to do that, but sometimes for the like key equations you're talking about, the mouse was not moving. I think also there could be an issue with Zoom as well, that I think sometimes if you leave your mouse not moving on your screen for a while, I think it disappears from the people who are seeing your screen share. So at least I think some people have told me that in the past. So if you're trying to point something out with Zoom, maybe it's good to keep moving your mouse around that thing as you're talking about it, just so that you make sure that I don't know if other people have observed that, but it seems that sometimes if you stop moving your mouse, like the person who's presenting and sharing your screen, it will disappear from the screen share. Like other people don't see your mouse. It's only when you move it and then for some period of time after it's been moved, it stays there. But then after a while, it gets hidden again. I guess because maybe it could be annoying if it stays there. So after a while, they remove it. Anyway, so that was the next feedback I would give. Maybe the last suggestion would be like on quite a number of the slides, you were sort of reading more or less the sentences that appeared on the slide. That would be something you'd really want to avoid in a presentation, because if you're reading the slides, it's kind of boring for the audience. Because if you think about it from their point of view, if you're going to mostly read the slides, then you can just print the slides, give it to the audience, and don't give the talk, because they can read the slides on their own. Sort of the value that you bring to the presentation is the things that you're saying that aren't really there, like the extra, information you're giving. So you didn't always read. You did a good job, for example, sometimes when you're describing figures, because there was no sentences there, so you were talking and you did a good job there. But a lot of the places where you have sentences on the slides, you were just kind of reading the sentences, and that's kind of boring for the audience, and it causes them to lose focus on what you're saying. Sometimes people recommend not using sentences on slides, because then you can't read it. Like if it's not complete sentences, you can't read it, so it kind of forces you to have to think about the words you're saying. But I wouldn't go so far as to say you shouldn't have sentences, but some people would say it's maybe better not to. And also, I guess one other advantage of not having sentences is it makes the slide a little bit less cluttered. So it's easier for people to kind of digest what's on the slide while you're talking if there's less text there. That said, though, some people prefer to have like kind of more verbose slides, but it's just something to be aware of. There's a little bit of like subjectivity or opinion involved in that aspect of like the particular comment I'm making. And then just one very minor feedback I have, which might have been that I just missed things, but you were on one of the slides, I think it was called Laplacian Matrix. Maybe it's this one here, I'm not sure. You talked about degree matrix, but I wasn't sure if you introduced the definition. You might have, and I probably just missed it. But that's a very minor thing. Just, okay, you did introduce it there. Okay, I just missed it. Yeah, anyway, because it's a common mistake for people
Yeah.
when they're giving talks, they assume some term is known by the audience when it's not, but in this case, clearly you presented it. Anyway, but just something for everyone to sort of be careful about is be careful if you're using any terms and things like that, that you don't assume too much about what the audience knows, and be kind of cautious. And if you're not really sure, just assume they don't know the term and present it. Because it never hurts you to present extra terminology and so on. The people who know it, they just go, oh, I already know that. But the people who don't know it, it's really helpful to them. On the other hand, if you have a term that you missed, you forget to present, then the people who don't know it, they just get lost and they can't follow your talk. But anyway, this wasn't the case here, but I just make that comment because it might help some other people here in their future presentations. Anyway, that's the only feedback that I have.
Okay.
Were there any other feedback from anyone else or questions? Again, sometimes feedback is very helpful as well. Like, don't just limit any, if there's any things, and sometimes it's your opinion, right? Like, everyone has a different opinion about what they like in terms of style for presentations. But if there's feedback you have in terms of things that, in your personal opinion, might make the talk better or improve the speaker's, presentation skills, by all means, feel free to, interject them. Again, sometimes they're opinions, right? Just like some of the ideas I'm expressing, but sometimes it's helpful for the presenter to know those opinions, because sometimes they can still help them to improve their presentation skills. Okay, well, I guess there's no other feedback or questions. So thank you for your talk, Jonaki.
Thank you.
And I'll stop the recording now.
Okay.